So any questions from what we just walked through in that last demo where we were testing the means between two populations?
Off the top of my head, no, but I have to see it again for me to have anything to go off of.
Okay, sounds good. And so if you do have more questions, feel free to jump in, but we can also touch base next weekend as we're recording, because even I thought it was useful before we even begin the recording to just review any questions from the last class. Okay, so where we left off was how we would test the means between two different groups, and we were able to conclude that this was statistically significant enough because our p-value was actually much smaller than our significance level, which is essentially just saying that the probability of seeing a value at least as extreme as this is pretty certain to say that the mean is different and is greater than, because the p-value is so small. Is kind of how you interpret it at a high level, but this is telling us to the actual degree of probability of seeing a value at least as extreme as the one we saw. So this is saying it's very, very improbable, but because it's so improbable and we did see it, that means that we can be more certain that what we saw wasn't just due to random chance and kind of just random noise, that it was far enough away from the mean because the z-score was 3.54. That was more than 3 standard deviations away from the mean to get us to this p-value that is extreme. So these are different enough based off of the distributions and the mean and variance for us to say that that people who get approved have a higher income than people who get rejected, which if we had to show this to like a subject matter expert, I assume that it would make sense to them as well. So moving forward in our lecture, where we will now be turning more to chapter 11, which gets into some other tests where we'll actually be talking about testing variance now, where we've talked about means. And I show you this logical breakdown of all the different types of tests that one might want to get into when it comes to this inferential statistics. And this just shows that there are a lot of different tests depending on the identified problem, the type of question, what information do you have available about the population. And for now, we are talking mostly about some of the tests that we have circled here. But in the next class, we'll be talking more about this test for heterogeneity, goodness of fit. But we've also talked a little bit about Pearson's correlation. We can use this type of testing framework to test association between two variables. So can we test that these values are correlated enough? But right now, we've really been focused on this right side of saying, do samples come from the same or different populations? And you see here, we're getting into ANOVA, and we're getting into all these z-tests that we have at the bottom. So I bring this up just to kind of expose us to all the different things out there and also just define where it is that we are covering for now. And this next part of class, we will introduce a new distribution called the chi-square distribution. And this is used for testing the variance between a population. And this should be somewhat familiar based off of our studies on quality control, where we were trying to test the variance of production, for example. If there's too much variance in the weight, for example, we might say that this production is out of control. So we would use this type of measure of variability using this chi-square to actually test, is this statistically significant enough to say something, is out of quality control? So this is similar to when we had those control charts, but now getting a little bit more into how we would test this statistically. Because before we kind of just visualize it and we see these patterns and trends, but now we're going to more empirically define that type of relationship. And I also bring up here the F distribution. In this class, we won't talk too much about how to use it, because that is when we test the population, the ratio of two populations and their variance, where the scope of this class will just be talking about estimating the population variance itself. But if we wanted to test that the variance between two populations is statistically significantly different, we would use the F distribution. And the textbook has information on that, but we won't have any assignments from it. I just want us to think about this and how it could be applied in other situations. So talking more about how this might be used, specifically, I think quality control is a good way to establish our understanding, especially relating it back to the business world, where there's always some type of quality control. Everything should usually be monitored in some way. We don't want to just be outputting something and not really knowing how does it differ to the other things that we are outputting. So even just one example, in machine learning, we need to monitor the quality of our models in the field compared to when we created it on our desk. So being able to compare, perhaps there's some type of drift that's existing in the model when we apply it into the real world. And we might create some type of quality control monitor to say, like, if our performance metrics go below a certain level, we would want to retrain the model and retest it and maybe like update it. Maybe, there's new data out in the world that we should take into consideration. But this quality control concept is relevant to, I would assume, most business fields. And I just brought up an example of how it applies to my life as a data scientist. So this type of quality control for an ongoing production process, we want to make sure that we should test, is there too much variance in this population where we might say something is out of control, or in this case, maybe I need to retest the model because our performance metrics are varying too much from the expected value. And I bring this up also because this is how we're testing using the chi-square to test the variance of the population. So we use this estimate of the mean and we use the estimate of the variance in this formula. And we'll talk more about how the distribution is used, but we should think of it a little bit more similar to the T distribution, given the shape of it not really being super normal, but having this long tails, where we also use degrees of freedom in order to define the scope of that distribution. So you see here on the right, depending on the number of degrees of freedom, where we have K here, where you'd have more of a flat or this kind of more asymptotic relationship in the distribution. And similar to any probability mass function, we've seen that this distribution is the sum of, well, in this case, it's the sum of squared normal variables. So it's always kind of this sums up to the total probability. So in this case, we're looking at this squared normal variable because we're looking at variance. So we talk about this sampling distribution where we're using the number of observations times our sample variance. And we use the degrees of freedom to, similar in the last class when we introduced degrees of freedom, we want to account for the amount of information that is free to be different. So again, thinking about you're a hat loving person and you want to choose what hat to wear, a new hat each day. If you only have 7 hats and on day 6, you really are only left with 1 hat. This applies that same constraint in degrees of freedom to the total number of observations again. So we use this degrees of freedom where it's the total number of observations minus 1. And we need to use this if we're going to use the chi-square table, where it is similar to that T distribution, similar to the Z distribution, where we have this family of distributions, and we can have a table that pre-computes the value that we should have as the probability for this area under the curve, given the values we're looking for and this degrees of freedom. So I think degrees of freedom, it was brought up by Darren earlier, kind of when do you want to use this? When should you use it? And again, it kind of depends on how you're calculating things. So that's why it's just good to be careful when you are using a function in Python to make sure that you're using it the appropriate way, because sometimes it might need degrees of freedom. Other times it's just the value of n of observations, and it already does that computation for you to subtract 1. But when you're using the table in the back of the textbook, you would take the number of observations and subtract 1 to have this degrees of freedom. And we'll talk through how you calculate that in the next slide using the table. And what we saw in this last one, where we have this positive skew, even if our number of degrees of freedom is small, we see that most of the values are to the left, and then you have this long tailedness to the right. And the extent of the skewness depends on the degrees of freedom. So the larger the degrees of freedom are, it starts to appear to look like a normal distribution, which was very similar to the T distribution as well. And so here is what a representation of it would look like. And we would calculate it in the same approach as we did for the other distributions, but we just use this different table, and we use the degrees of freedom and the value of alpha. So a lot of this should be similar, just slightly different, because we'll be using this chi-square, which measures the variance compared to something like where we were talking about with the Z table and the Z distribution, or the normal distribution that uses the Z table. So as I was mentioning, we use this area under the curve in the exact same way, just the values will be different. And this allows us to now make inferences about the population variance. And subsequently, because if we know the variance of the population, we also can then calculate the standard deviation. And we can use our confidence intervals to be able to infer what is the population variance and standard deviation based off of the sample we take. So this slide is just showing how we use the area under the curve in the exact same way we have been, to use the tails to define the probability of seeing a value at least as extreme as these different values we have here in this example. And we use that area under the curve to say what's the probability that a value would fall in either direction of the tail. Any questions before we move ahead?
No.
Okay. So now we'll talk about the confidence interval formula we'll use for this. So when we want to calculate this population variance, again, it's a lot of similar inputs as we've used in the past, where we have the value, the number of observations, but in this case, we're using the sample variance. That's what this S squared is. So, and it should start to look familiar when we don't have that squared. We're using the standard deviation, but when we do have the squared, it's the variance. Because that's just how the formula works between variance and standard deviation, where we take the square root of variance to get standard deviation, or we can take the square of the standard deviation to get the variance. So just explaining a little bit why these numbers we see here. And then we have this chi-square represent the test statistic we would use. And I think before I get to the demo, we should have a formula, kind of how we would, yes. So before we get to the demo, I just want to talk through more how we would see this, and then we'll finish the class running through the demo for how we would calculate this variance. And I bring it up here, again, from the same quote, how this applies to real world. We'd rather be vaguely right than precisely wrong. And I bring this up again because variance is very often used for understanding risk in different investment strategies. If there's a lot of variance in what the return is of your investment, you might have higher return, but there's this higher risk. So we would want to use this type of approach to understand how much variance exists in our investment, for example. And we can use this framework to know a vague rightness. We can't say precisely the variance will be this, but we have our confidence interval to give a vague rightness of what we'd expect the variance to be. So just tying together these concepts and bringing it back to how this would apply to real world. And we use these different options for our different testing. So if we're trying to test that the variance is equal to a certain value, we would use a two-tailed test. If we want it to be less than or greater than, we would use the right or the left-tailed test. And if we were getting into testing the population variance proportions being different, we would use something similar to what we just learned today, kind of in that similar framework of testing if the means are similar or different and by how much. We would just use that type of framework to test the variance, and we would use the F distribution. That's kind of just an aside of how you would take this and run with it outside of the scope of our class. But for now, we are using this variance, which is very similar to what we learned last class when we were just testing the mean and seeing if the mean was equal to a certain value. So now we're using this type of variance being equal to a certain value that we would expect. And this would be how we would calculate that test statistic, where we would have the number of observations, our sample variance over the population variance, and we would use these degrees of freedom to calculate if we were using the table as well. So I'll walk through it, and then I have a slide here where it shows using the table, and then the demo will walk through how we use this in Python. So this is an example talking about the same data set, I believe, or probably very similar when we were just starting to talk about variance, when we had this growth versus value fund. So similar concepts where I think growth was that the return was much higher and perhaps there was more risk, where the value had less variance. So feel free to review some of those distribution plots we made where we kind of were testing outliers as well. But in this scenario, we are trying to see if the standard deviation of returns for the growth fund exceeds 20%. So, and we have standard deviation here, but that is just equivalent to the variance exceeding 400% squared, essentially. So we just take 20 and we square it to get 400. And if we were trying to test the variance, we wouldn't need to do this. Or, if we were trying to test the standard deviation, just depending on what we're testing, we would either square it or take the square root, because these things are two sides of the same coin. Yes.
I just trying to use the raise hand feature for once instead of interrupting again. So for this one, would it be similar to the last one where it's mean 1 minus mean 2, and then we do greater than or equal to, or in this case, it would be exceed. So I guess the mean would be greater than 0 or whatever the number is supposed to be.
So this should be more similar to what we started off in last class compared to what we started in this class, because what we started in this class was comparing two different means.
Oh, okay.
Because we had like the NASDAQ compared to the S&P 500, and we're trying to say one had more diversity than the other. In this case, this is more similar to last class where we had just one, population, and we're trying to see if the standard deviation in this case compared to mean for this one population exceeds or is equal to a certain value.
Got it. Okay. So I guess it would be for the null, which is 0, the top one, right?
Mhm.
It'd be the mean would be greater than or equal to the 20% or 0. No, damn.
So it's, I think, kind of like the opposite usually of what you would want to be testing is the null hypothesis. So in this case, we wanted to test that the variance exceeds this amount, 400% variance. So we would want to test everything. You know, we're trying, our established understanding is that it's not this great. So we need to find evidence to say, hey, the variance is actually larger than this value. But it could have been equivalent if you were trying to just test the standard deviation, if you use 20, but then we wouldn't be able to use our formulas here because all of this is in base, is in the variance. So you could, if you really wanted to test the standard deviation, you would need to change the formula to be about standard deviation, but it is likely more straightforward to translate everything into variance so that you can use the formula that we have here and then just take the square root to get back to the standard deviation. But I think, you know, your thinking was generally in the right track when it comes to how we would test this, and that we're only using one, you know, sample here. We're not comparing two different groups. And so that's why it would be this type of format. Does that make sense?
Yeah, I was vaguely wrong.
Yeah. Well, yeah, at least you weren't precisely wrong. Any other thoughts before we go ahead? So this is just kind of setting us up for how we would frame the question. Okay, so this is how we would calculate it using our test statistic. And then also what I was referring to when we would want to use the table in the back of the textbook compared to using something in Python to calculate it. So we have just our, you know, our input parameters that we're using of n equals 36 of the number of observations. And so see, the formula subtracts it to make it into degrees of freedom for you. So that's kind of, that was the question of, do I need to input with the degrees of freedom or not? And the answer is it depends on like which formula are you using and how are you computing it. So just kind of know that we are usually taking this degrees of freedom whenever we're taking the number of observations and subtracting 1. And this just allows us to use all these assumptions because we can't have total, like you can't know which hat you're going to wear on the 7th day. Like you don't have the decision in it. So we need to just subtract 1 so that we can still use all of these formulas, because it would essentially just kind of not allow us to use these if we had without the degrees of freedom accounted for. And we use this sample variance that we would take. So if we had that data set of, and I think that's what we have in the demo, where we have just a sample of all returns for the growth fund. And we would see, so here we have the standard deviation equaling 23, but we square it to get the variance and divide that by our hypothesized value of the variance. And that gets us to this test statistic of 49.56. And then we use this table as well, which kind of shows us what value we would use for, it's essentially calculating the same thing if we had the degrees of freedom that we're looking for. So in this case, we have that value of 36 minus 1, which would be 35. And using this distribution, we can actually just use our alpha value. So in this case, we were saying like statistically significant at either of these values for a one-tailed test, since we're just trying to see if it exceeds this value. And we would use somewhere right in between these values. But this kind of gives us more of an approximation. We're using the test statistic, and the formula gives us that exact value. So now I will turn to the demo where we will walk through a similar problem for testing the variance.
At
Nat,
the end, can you show us the I'm sorry, I should have raised my hand again.
no worries.
At the end, could you show us the table as well, if you don't mind?
Yeah, let's start with that as well. So it's a good refresher. So I have the textbook open here. And I think this is exactly where I'd want to be. So you'll see a lot of the content I had in the slides is pretty much directly from the textbook when we have any of these formulas who are here. So it could be helpful just to review using the textbook as well. And it also walks you how you would use the table. So I will just show that now in case folks want to use the table as well, just to validate what we do. So it has it here in Appendix B. Oh, let me go back to where we were. Okay, because that Appendix B just brought us, let me make a duplicate of this just so I don't get lost when we go back and forth, because it was in table 3. And this walks us through what we had before for the chi-square value. So I just have this duplicated so we can get back to it. So let's go to table 3. Oh, this just gets us to that, but I guess it's it. Okay, so back to Appendix B, but this is table 1 with, this was the normal distribution, the normal curve. This was, when we're using just the other side. So it's kind of cool to see how now we have covered the normal, we've covered the t distribution, and now we are at the chi-square distribution. So that's why it's in table 3. And what we saw before when we had that value of 36, I think it was back to the slides, just so I can show how things were all connected. So we have this value of 35 because our n was 36. So if we wanted to use the table in this case, we have degrees of freedom, which was number of observations minus 1. So that's why we use 35. And let's just say we wanted the area under the curve. If we wanted to test this at a significance level of, 95 or 90, if this, is a one-tailed test, we would use one of these two to get that value of the test statistic, which is what we saw before. Does that answer your question about how the table works?
Yes.
Okay. Which I've really been appreciating students in the homework when you have both how you would do it in Python and then also using the table as well. I think, it's great just to show you can handle this type of problem in lots of different ways. Okay, so let's run through this example where we have this. Let me just get us set up where I think what we're doing here is just kind of walking through an example without any real context around it. We're just going to try to analyze how we would find the value x for a specific value. So this will be very similar in the homework where there's not necessarily like a whole case study around it, but you just have, like give me the test statistic based off of the inputs. So in this case, we're trying to test for this upper tail of 0.25. So if we were using like the table, we would use this value of degrees well, that doesn't make sense for why that would be up here, because this is more like the alpha rather than degrees of freedom. So that doesn't necessarily like label what this is horizontally, but we're trying to test for that value of alpha. And let's just say degrees of freedom are 5. So if I had more context around this, I would have defined these types of things. And let's just say our value of X, we're trying to see for if it's greater than 85, but I'll have to, once we walk through this, I'm sure it'll make more sense why I have this here. But right now we're just trying to use these different inputs, and we were trying to get the p value from this type of input. So in homework, you'll probably see something like this where they just define stuff. So I assume that's what I was working from. I just don't have the context around it. So I'll go back and put it there once I find it. But this is what that distribution looks like. We drew this using the value of X, which just creates values from 0 to 20. And all we need are these degrees of freedom, and it creates that distribution for us. So we have this 5 as our degrees of freedom. And so that's why it's a little bit skewed in this way. And that's just because of the way the chi-square distribution works. And similar to when we use the normal or we use the t distribution, it's all very similar where we have this stats package. But this case, now we have this chi-square continuous random variable. And it's because we're using this family of distributions from the chi-square. So we use this upper tail to say like how much area under the curve. So this was just defined for us. And we subtract 1 from that because this returns the cumulative density function up until that value. And we use our degrees of freedom here for this formula. So that's why when you were asking, like, when do we use it? Again, it kind of just depends on the function you're using. So in this case, for the chi-square, we needed to define it here. And now let's plot what that looks like and what value we're trying to test for, where we're trying to see if the value falls in this region for us to say that there's something significant here. So this kind of makes more sense. I think this was just an error, actually. I don't know where this 5 came from, where it should really just be 8, because maybe that's what we're testing for. Let's just keep running and see what happens. Because this is now slightly larger, where 8 is the degrees of freedom. Because actually, really, this should, okay, now I see. This was the value of 5. This just shows us the difference when we have 5 degrees of freedom compared to 8 degrees of freedom. And the purpose of this demo is just to show how the distributions change, where now it's a little more normal looking because our degrees of freedom are higher. And we use, but this should really have 1. Well, now because we're looking for the lower tail, we don't need it. So this is just talking through as if this was another example. Like in the textbook, you'll see homework that looks exactly like this, where now this is less than, where this one should be greater than, for us to just follow the rest of the tutorial, what it is we're doing here. And so now we don't need to subtract from 1 because this is now lower than a specific value. And now we're just testing underneath this area. And we use that value of P. So this was just to show how the distribution looks, how depending on the value we are testing for and the degrees of freedom, how we would use either this formula to get that test statistic, or if we're using the table in the appendix, it should come out with the same values. And I see we have about 4 minutes left on this, and I think we can get through the rest of it. But if not, we'll have to just rejoin one more time. And for next class, I'll look into how I can make it so that we don't get constricted by our time using Zoom. I'll find a better platform. So this is from that sample and that we walked through in class where we have this growth versus value. And now we're trying to test the variance being different. So this example follows exactly from what we were talking about. This is trying to find just the confidence interval for the population standard deviation for both funds. So this just uses what we were learning to create that value on the chi distribution to actually just ascertain what is the likely variance if this was just a population. So that's why this was saying, this is only 36 rows. So I guess it was over 36 years. It just took one snapshot. So that's not, the population of every single day. It's just a sample. So from this sample, we will calculate the population variance. And we'll use this 95% confidence interval. We use these degrees of freedom when we're using the same exact thing that I just walked through earlier when we just had those inputs to get what the upper and lower tails are. And this is just using the formulas from the textbook to calculate the lower and upper bound based off of the value we have. And so that's using the sample standard deviation, and therefore it outputs everything back as standard deviation. So we need to take the square root to get it back. Well, this gets us in variance. We need to take the square root to get back to standard deviation. So this is telling us that the standard deviation of the growth fund will be between 19 to 31% return using the chi distribution and our upper and lower bound for confidence intervals. We can now say with some degree of vagueness where our value might fall. And this is just using the same function I have above. And now for the growth fund, and we see the variance is slightly lower. And when I say variance, I should be saying standard deviation here because we took the square root of the values. So this is pretty much saying that the growth had a wider confidence interval because this 14 is less than 19. So this is essentially going a little bit more varying to the left-hand side, but not as much on the right-hand side for the value. So this growth, it would be interesting maybe to plot this. And so because we have less than a minute, if folks want to rejoin a third time, otherwise I will post the recording and we can walk through this last example. So I will stop my screen one more time. If we just want to maybe walk through this and then come back for questions. This is me just using what we walked through for testing the different statistic. And if the value is less than this formula, this function pretty much gives all of the different inputs that would be required for testing if you should reject or not reject the null hypothesis. And this just packages everything together. So perhaps we'll end the class